Hey everybody, I want to show you how to do the last kind of chi-squared hypothesis test that we're going to talk about. It's actually the simplest one by far. It's just very different than the others, which is why I left it for the last. I didn't want to lead with it because that would make it seem like, oh, this is the basic kind when it's not. So um, here's the idea. It's called the test of a single variance. It is very, very similar to just the one sample hypothesis tests that we've done in the past. So here we go. All you're doing is you're checking to see if one sample has a standard deviation or variance, or we're actually testing variance here, which if you recall, a standard deviation squared has a variance that is significantly different than a hypothesized number, right? It's exactly like a one sample means test. You have to do it with quantitative data, numerical data, because you have to be able to take the standard deviation. You have to be measuring the standard deviation of something, and you can't measure the standard deviation of categorical data. And again, I'll remind you that if you're thinking, well, wait a minute, we have standard deviation when we do one prob z test, we have a standard deviation of the sampling distribution, but not of the data itself. Whereas here we have sampling distribution of, we have the standard deviation of the data itself. That's the thing that we're measuring here. So there's not really too much to say about it other than the test statistic is 100% different, right? It's completely different than the test statistic for the other cases, right? It's just this n-1 s squared over sigma squared, and sigma squared is going to come from your null hypothesis, because we are doing the standard one sample test of we're going to compare something, we're going to compare some statistic about our data to a hypothesized number, which is going to be in the null hypothesis. Yeah, I don't really want to say too much more about that other than this. It's got n-1 degrees of freedom, so you can get a lot more degrees of freedom in a test like this than we will in most of the chi-square tests involving tables, right? Those are going to be, 10, 15 degrees of freedom. This can easily be hundreds. And unlike the other ones, this can be right-tailed, left-tailed, or two-tailed, depending on what your alternative hypothesis is. So if your alternative hypothesis is less than, right, if your alternative hypothesis is that the standard deviation, the variance, I'm going to go back and forth between standard deviation and variance. Just remember, standard deviation is just the square root of variance, and variance is just standard deviation squared. What was I saying? Oh yeah, if your alternative hypothesis is that your variance is less than a certain number, then it's going to be left-tailed. If it's that it's greater than a certain number, it's going to be right-tailed. And if it's just different than a certain number, then it's going to be two-tailed, just like before with the one sample test. So this is actually a really simple test statistic, and in fact, your calculator doesn't even have a test for it. Like there's no, if you go look in your calculator, there's no like test of a single variance that they do. So I'm just going to do this thing in sheets. Yeah, I'll just do it in sheets. It'll be relatively easy. We use the chi-square distribution, chi-dist. I don't remember what the exact command is. We'll see when we get there. Yeah, let's do it. We can do this one. I'm gonna leave this one, I think, and do this one, which is a little bit more straightforward. If you want to see me do the other one, you can come ask me in office hours. I'm happy to do it. All right, so here we go. Stephanie is manager of a bank. Oh, I just realized I used the same name for this bank manager as I did for the one I did on the homework where she's testing her laser. Anyway, she's a manager of a bank who apparently likes lasers. She thinks that customer wait times might be more consistent if she changes her line system. She currently has the bank set up so there are several small lines, and she's noticed that sometimes a single customer of a very long transaction causing all the people behind this customer to end up with long waits while other lines move quickly. Stephanie's guessing that if she changes to one large line, the fast and slow customers will even out more, and there will be fewer long waits for individual customers, which of course would make them mad or at least annoyed. So she already knows from a variety of previous experiments, because she likes to do statistical experiments in her bank, that the average wait time in her bank is 3.6 minutes with a standard deviation of 6.1 minutes. And notice that's a pretty big standard deviation there. And that the wait times are normally distributed. Test her theory about the lines. Stephanie rearranges the lobby to have one big line. She has an intern go through all the security tapes for 3 days and time the customers, because that's what interns are for. In the 3 days, the bank serves 302 customers who have an average wait time of 3.4 minutes with a standard deviation of 4.8 minutes. Okay. So we're going to use a significance level of 5%. Is this enough evidence to suggest that Stephanie's rearrangement of the lobby has reduced the variance of wait times, or put another way, has made the wait times more consistent among customers? So notice that this is not a question about the mean. This is a question about how variable the wait times are, which is standard deviation or variance. And so that's what tells you to do a one sample test of a single variance. I'm sorry, that's what it's called. So let's go set up a whiteboard. Do this test. So she wants to know if it has reduced the variance of wait times. So our null hypothesis is going to be something, and our alternative hypothesis is going to be something else. So we know that this is going to be about sigma, or it's actually going to be about sigma squared, because the test of variance has the squareds in it. So you can write this in a couple of different ways. I'm going to do it like this. I'm going to say that my alternative hypothesis is that the variance is lower, right? Sigma squared is less than, what was it, 6.3? I should really remember this stuff before I jump in here. 6.1 minutes was the old one, was the old variance. So let's put that down, less than 6.1 squared, which is something, it's like 37.6. We'll worry about it later. I actually kind of don't care what the number is. I said that, the way I said that made it really confusing. I do care what the number is. I'm not going to worry about squaring it and writing it out, is what I'm saying. 6.1 squared is a fine way to put it, is what I'm trying to get at. And then the alternate, or excuse me, the null hypothesis, sigma squared greater than or equal to 6.1 squared. Okay. So yeah, got my test statistic. We can figure out here. I'll sketch out the graph. Let's do that in black. Sketching the curves in black. So it is a chi-square curve. So it's going to look, roughly like this, like a maybe slightly right skewed normal curve, and that does not go to the left of 0, because again, it's still chi-squared, so it still can't go left of 0. So this is chi-squared with, or square with 301 degrees of freedom. Is that right? 301. Yeah, 301 degrees of freedom. Chi-squared 301, which makes it look very much like a normal distribution. And that also means that the mean, which is pretty much at the peak, this is basically a normal distribution, the mean is going to be at 301. Maybe about there. So we are going to do this. We're going to say chi-square, our test statistic, equals n minus 1, which is 301. 301. You know what? Let me actually write the formula here. N minus 1 times s squared over sigma squared. That is our test statistic. Sigma squared comes from the null hypothesis, of course. It's going to be 6.1. S squared comes from our data, which was 4.8, I believe, was our standard deviation. And n minus 1 is, of course, n minus 1. So it's 301, 301 times s squared, which is 4.8 squared over sigma squared, which is 6.1 squared. So we'll go calculate that up. Let's see what that is. Let me share up my, sorry, I've got it. I had some confidential information there. I have to pause this and go get it all set up. Pausing. Sorry, I was just realized I had the grade sheet open, and it is technically a HIPAA violation if I let people see the grade sheet, because that's confidential information. So yeah, I gotta be careful about that stuff. So anyway, there we go. So I'm gonna find this value and then put that on my distribution and shade to the left because it is less than. So let's go find this value. 301 times 4.8 squared over 6.1 squared. We will just share a spreadsheet here. So this is equals 301 times 4.8 to the second divided by, oh, I gotta be careful with the parentheses here. Let's make sure I get parentheses around the right things. I don't know how it does parentheses. 4.8 squared divided by 6.1 to the second power. We get that number, 186.375. So I'm going to use the chi-distribution. I'm going to go to the left, right? So 186.375. So let's go put it. Now, I will mention that number seems big, but it's not actually. That's actually a relatively small number. Right? So this was like 186.75 or something like that. It's less than the mean, right? The mean is 301. So finding this 186.75 is really not that big a number at all. So I'm actually expecting, well, we'll see what the p-value is here. Actually, 4.8 seems like it's a long way away from 6.1. So and 301 is a pretty big sample size, or 302 is a pretty big sample size. So I'm expecting to be able to detect this difference, and I'm thinking that the p-value is likely to be pretty small. But let's go have a look. So I want to do from 0 to 186.75. Or I'll just use this, right? 0 to 375. Sorry, I messed that up. It's actually 38. Let's have that actually be the right number. No need to have this be bad on a video or whatever. 0.38. There we go. Okay. All right, so we're going to do equal chi. Is it chi dist? It's chi dist of one. Well, I'm just going to call it A1 with 301 degrees of freedom. Do I need it true? Okay, so it's the right-tailed chi-square distribution. Huh. So this is the area to the right. So I actually need to do 1 minus this. Right? It says it does the right tail distribution. It's funny. I just assumed it would do left tail like it usually does for the other ones. Like I figured I was going to have to tell it that cumulative equals true, but apparently not. We won't do that. There we go. Okay, that number is real small. That is 0.00000003016. So what is that? 1, 2, 3, 4, 5, 6, 7, 8. 3 times 3.02 times 10 to the negative 8, which is real tiny. So we get we call that chi-square CDF if we want to do it on calculator. But I will just say this is chi dist. So it's 1 minus chi dist of 186.38. My 8s are looking especially bad today with 301 about equal to 0. Well, I'm just going to use scientific notation. It's just so much shorter. 3.02 times 10 to the negative 8th power, which is absolutely tiny. So that is less than any reasonable alpha. I don't remember what alpha we were using, but it kind of doesn't matter, right? If it was 5%, this is less than that. If it was 1%, it's less than that. If it was 1/10,000th of a percent, this is still orders of magnitude less than that. So we're going to be rejecting our null hypothesis for sure. So that means that we think that the variance of wait times among customers in the bank has decreased. That it's smaller than it used to be. So that's what I'm going to write for my conclusion. Let's write a conclusion over here in text. Conclusion. This experiment suggests, I'll make this text a little wider. Experiment suggests that one big line does reduce the variance in wait times at Stephanie's bank. There's my conclusion. Seems pretty straightforward, right? And again, as always, just a reminder, the way you want to write your conclusion is to say the hypothesis that you think is true, but in plain English. So the thing we think is true is the alternative hypothesis here. I think that the wait time or the variance in wait times has been reduced from what it used to be. There you go. That's my conclusion. So let me head on back to the worksheet here because I want to make a quick point. Which do you think is more important to customers, average wait time or variance of wait times? I actually think it's variance. I know I put that in a note here, but let me explain. I actually think it's variance of wait times. If you go to the bank and there is a 5-minute wait, that's not so bad. If you go and there's a 10-minute wait, you probably don't even really notice the difference that much, right? Like you might be getting a little more annoyed, but it's probably just however long it takes to wait in line is going to feel like, yeah, it was a little bit of a wait. However, if you go to the bank and you see a bunch of people getting helped really quickly and you're not, that is annoying. Everybody hates that. So I suspect that having some customers get served really fast and some get served really slow is going to lead to a lot more grumpiness than everyone getting served at, roughly the same pace, even if that pace is slightly slower. So there you go. That's my hot take on variance being probably more important than mean to the customer experience. Yeah, I think that's kind of all I really wanted to say about test of a single variance. It's pretty easy to do. You can do it in your calculator. If you go to if you go to stat and tests, there is no test of a single variance in there. You have to do it sort of manually, but it's easy to do manually. It's literally just this, then use chi-square CDF. That's it. Yeah, I don't have too much to say about that. I do want to have a quick recap of the various hypothesis tests that we looked at, because I want to talk very briefly about that. So the ones that we looked at were chi-square goodness of fit test. So goodness of fit is very much like a one sample test in that we are comparing our data to a fixed number, except it's not just a fixed number, it's several fixed numbers, right? So this is comparing data to, or comparing several proportions to, how can I say this? Comparing several sample proportions to several given fixed proportions. Contrast that with a test of association or independence, which contrasts two things with each other, essentially, right? We can have two variables. Up here, we only have one variable. In the case of this first one, it was eye color, right? We have one variable and we're testing to see the distribution of that variable. Does that match the distribution of the color? This, we've got two different variables and we're not testing to see if one of them matches the distribution of the other one. We're testing to see if the two of them are related to each other by well, I won't go into it too much, right? Like you heard the long-winded explanation back when I gave it in video number 2 here. But we got two different variables that we're testing to see if they're related to each other, which is sort of like a 2-sample test. It's still only one sample, but like you're not contrasting one set of data with just a fixed set of numbers. This is contrasting two sets of two variables within the same set of data, right? So sort of like a 2-sample test, at least conceptually. And tests of association are always like that. Like the homogeneity ones that we talked about very briefly afterwards are exactly the same thing. It's still testing to see, presence of alcohol versus severity of injuries. Are those two things related to each other? And then the last kind that we just talked about was test of a single variance, which is very much back to the 1-sample case. And in fact, it's like an even simpler 1-sample test than the goodness of fit test. It's just testing something entirely different, which is the variance. You're testing to see if your population variance is different than expected, right? And so you have to start with an expectation of a number for your population variance, and then you take a sample and you compare your sample variance to that number and see if it's much different, or see if it's different enough to make you want to believe that that number you originally hypothesized is actually wrong. So there you go. Very simple test statistic too, like not much to calculate. It's not the whole sum over all cells O minus E squared over E, nothing like that. It's just that sample variance happens to have a chi-square sampling distribution. So that's why we use chi-square for tests about sample variance. Yeah, I think that's where I want to leave it. I'll go ahead and post up this worksheet. This is a worksheet that I made for my previous stats classes that weren't taught exactly the same way, so things are going to not precisely match up with the way I explain them in the videos, but it should be close enough. I think it's a good enough approximation. You can look in the book too. The book also does the whole independence versus homogeneity thing. They seem to care about it. I used to as well, and no longer do. Just call it a test of association. That's really what it is. Anyway, I'm going to go ahead and stop the video here. Thanks for watching, and I'll see you guys in the next video.